Welcome back to Protovenix SystemVerilog series. Today, we'll explore three advanced constraint topics: iterative constraints, constraint mode control, and static constraints. These give you fine-grained control over how randomization behaves. An iterative constraint applies the same rule to every element in an array. We use the for each construct inside constraint blocks for this. Here's an example. Class packet, rand bit 7 o'clock, address 5. Constraints _iter for each address, I, less than 100, in class. This ensures every element of address is randomized below 100. Iterative constraints make large data structures easy to handle. Sometimes, you need to temporarily disable certain constraints. You can do this using constraint underscore mode and re-enable them later with constraint underscore mode. Consider this example: class packet, rand bit 7 o'clock, address, constraint C underscore address, address less than 50, in class. Then, packet P equals new, initial begin P dot underscore address dot constraint underscore mode, // disable constraint void, // address unconstrained P, underscore address dot constraint underscore mode, // re-enable end. This technique is handy when running multiple test configurations or generating both constrained and unconstrained data. Static constraints are applied at class definition and cannot be changed later. They are evaluated once and remain constant throughout simulation. For example, class config, static constraint C underscore static, a less than 10 in class. The constraint block locks and glows, symbolizing its immutability. Static constraints are useful for defining fixed configuration limits that don't depend on dynamic variables. To recap, we covered iterative constraints, which apply rules to each array element, like for each ARR I100. We also discussed constraint mode, enabling or disabling specific constraints using C.constraint underscore mode. And finally, static constraints, fixed at compile time and unchangeable, as seen with static constraint C, a less than 10. Master these constraint techniques, and you'll be ready to build highly flexible and intelligent verification environments. Next up, constraint randomization debugging tips.